Okay, which is kinetic of particles. Okay, kinetic of particles from Hibbles book, or not, from Beers and Johnson. Okay, so in a nutshell, what you have learned, okay, for this chapter, okay, I just to give overview of what we have learned, okay, for this chapter is we cover about Newton, okay, we cover about Newton's second law. Let me write it down. Okay, so in a nutshell, okay, in summary, we covered Newton's second law. Okay, Newton second law. Okay, which is summation of force, right, equal to mass times acceleration. Okay, this is what we have covered. And you also be introduced to number one. This is number two. We cover the concept of linear momentum. Okay, we have covered what concept of linear momentum, right? So concept of linear momentum is summation of force equal to L dot, right? So basically linear momentum, concept of linear momentum, we have mentioned just now, L equal to, okay, mv, right? So in this case, we have the resultant force acting on a particle is equal to the rate of change of linear momentum of the particle, right? So what are the concept lagi yang that we learn? Another one is number 3. Number 3, you learn about equation of motion, right? Equation of motion of particles, okay? Okay, equation of motion of particles. So as for rectangular component, okay, so you have summation of force, okay, in x direction equal to max, right? Summation of force in y direction is may, right? And summation of force in z direction equal to ma z, right? Correct. Correct. And then we have another one using normal, using tangential component, okay, tangential component and normal component, okay, and normal component, okay, and normal component. The one that we take our class time today, just to look at that concept, right? So you have summation of force, okay, tangent, okay, you have m dv dt, right? And then this is for tangential, so this is for normal. So you have m B square over rho, right? Okay, what else that we have learned just now? Still remember? Just recap, just what we have learned just now. They have done equation of motion. Anything? Transverse. No, that one we have covered just now. Equation of motion. Any other answer? Just to recap what we have learned. The important equations. How come? Should you remember the topic that we learned today? Angular momentum, right? Yeah, correct. Good. We talk about angular momentum. Okay. So angular momentum, just to recap what you have just now. So we have the concept of angular momentum, right? So the concept of this one, remember the equation H dot equal to position vector R, and then, right? And then you also learn about rate of change of angular momentum, which is summation of moment equal to H dot. This is use different color. Which color? Red, huh? Red. Okay, rate of change, okay, of angular. Okay. And just now we mentioned about radial and transverse component. Okay. So basically these are the things that we have covered. Okay. Okay. Newton's second law, linear momentum, equation of motion of particles, and then we use tangential component and normal component and angular momentum. Okay. All right. For the next 20 minutes, we are going to go through the next topic. Okay. The next topic of today's lecture, which is the topic of kinetics of particle. Okay. Energy and momentum method. Okay. These are the topic that we are going to cover. Okay, for this topic, I think most of you in diploma level, you've been exposed to this topic. I think this is nothing new. Okay, except we're going to go through to recap the important concept, and then as usual, we're going to do a few examples to strengthen the fundamental that we have learned. Okay, so we are here now. You have completed the topic of kinematics. Okay, kinematics of particle. We covered rectilinear motion, curvilinear motion, the relative motion, and dependent motion. And we have completed covering the top kinematic of particle, which is Newton's second law. And now we are at this section, which is work and energy. Okay, work and energy. If you look at this figure, okay, look at this figure, we are having here work of the force, right? Work of the force. Okay, we have here the particle over here. The position vector from O to A is position vector R, and then you have the force acting to that particle. Okay, and then this particle is moving from one place to another, which is to another location, which is here, I name it as A prime, right? So the position vector of it will be as the following, which is R plus dr. Small changes in R, right? Small changes in R. So you have here A dr, right? You have from A to A prime, the distance from A to A prime is small differential, we call it dr, okay? Dr. So what is dr? Okay, what is dr? What is dr? Okay, what is dr? dr is what we call the particle displacement. Okay, particle displacement, which is you can write the dr vector. Okay, differential of dr, particle displacement. You move a bit, move a bit. Okay. Okay. Another question that I'm going to ask you: what is the work? What is F? F. Basically, what is F? And F is work of force. Okay, work of force corresponding to the displacement dr. Okay, it is work of force corresponding to displacement dr. Okay, just to recap, when we talk about work, okay, it is a scalar or vector. And what is the unit? What will be the unit of it? Right? So work is a scalar quantity, okay, of units Newton meter, right? Work done. Work done is force times distance, right? So in SI, it is in Newton meter, right? Okay, now we want to simulate the direction of it. Look at here, we have force, we have dr. If F and dr, they are in the same direction, okay? If they are in the same direction, so we can write here du equal to F ds, right? U is work done, force time distance, right? Du equal to F times ds. Okay, another question. If F and dr, if these two, they have, or they are in opposite directions, so what will be? What will be the equation? What the equation be? It's going to be what? So the equation will be in the opposite direction, right? So du will be minus Fd, right? So it's going to be du equal to minus Fds because it is in opposite direction. Okay, now I want to write work done from 1 to 2. Okay, work done, work of the force, okay, corresponding to the displacement. We want to write u from 1 to 2. Okay, so u from 1 to 2 is going to be force times dr. Okay, force dot dr. Okay, vector force dot dr. Okay, so you can to get f times ds cosine alpha, okay, equal to fs dx plus fy dy. Okay, this is the concept of work of the force. Okay. Are you following me? Do you have any question? I try to read your comment here. All right, okay. Right, all right. So we proceed to the next slide. Okay, the third criteria that I mentioned just now. What will happen if F, okay? What will happen if F is perpendicular to dr? Just not same, and then opposite. So what will happen if this force is perpendicular to this dr, right? So work done will be zero. Okay, will be zero, right? Yeah, it will be zero. All right, we proceed to the next slide. Okay, we look at the next slide. Okay, this slide shows you how we can look at the finite displacement. Okay, work of a force during a finite displacement. Okay, for this one, to explain the figure, okay, if you look at the figure, we have here, okay, to enlarge it, we have the figure, we have the particle, okay, we have the particle, here, this particle, okay, from A1, okay, from A1 to A2, okay, from A1 to A2, we want to find work done, okay, work done. To illustrate here, this is a work done of finite displacement. We have here point A, particle at here, particle A. We have force acting, okay, onto it, okay. So you have here, it will move along this curve, move along this curve. So this is S, S is the length of the curve. From here, we have S at point 1, A1 and A2. So at 1, from 0, this is S1, right? This is S1. To make it easier to illustrate. So this is S1, right? This is S1. The whole here, from 0 to A, along the curve, this is S, right? So at this particular point, point 1, so we have A1 here, okay? So we have here, this is S2, okay? S2 is here. So we have two positions, point A1 and A2. So to find the length of it, from here to here, this is S2, okay? This is S2, right? This is how we look at it. And then this line. Okay, this is dr, and this is ds. So what's the difference between dr and ds? What's the difference between dr and ds? From the figure. Can anyone answer? What's the difference between dr, this dr, and ds? Is it the same? ds basically is along. Remember the formula that you learned before, S equal to R theta? Long time ago you learned S equal to R theta, right? S adalah panjang lengkuk, right? Panjang lengkuk. The length of the curve, right? Ini lengkuk lah ni. This is lengkuk ataupun curve, right? This R is related to the position vector, okay? Which is, if you look at here, this is, looks like it's tangent to the path, right? Tangent to the path. This is the position R, right? In order to work to be done, you have to move to this place. Work equal to force time distance, right? If it is no movement, so no work done. That's why you need to be mobile, move from one place to another. So people will say you will work. If you work from home, meaning you no work done, right? Is that right or not? So it violates the formula, work done. Work from home, so no work done. So back to this one. So now you can differentiate between S and R. It's not the same. It's not the same, right? So we want to find or use this formula. So work done. This is how do we pronounce or write this one. So work done, kerja yang dibuat from 1 to 2. Okay, work done from 1 to 2. Okay, is the integration. Okay, f dot dr, f dot dr, and you integrate from here a1 to a2. Okay, that's what you did. Okay, so if you want to write in term of s1 and s2, so we can write this one in this form. F dr basically is f cosine alpha, right? F cosine alpha and then ds. So you do the integration and you will get S1 ft, which is f tangential. Okay, f tangential ds, you integrate S1 to S2. Okay, this is what it's all about. So if you want to plot work done, okay, by using the graph, okay, work done, which is area under the curve of ft plotted versus S. Okay, so we plot the graph, ft versus S. So work done is area under the curve. Okay, area under the curve, the one that been shaded here, right? This is area under the curve, been shaded here. This is work. Okay, okay, work done. All right. Next one. There are different conditions to illustrate this type of problem, workforce. Case number one is for the case of rectangular component, okay, which is this one. Okay, this is case, okay, this one. This is case number 1. Case number 1. The case for rectangular component. Work done from 1 to 2 in the case of fx dx plus fy dy. Okay, this is case number 1. Case number 2, we look at another example. This work done when we have a constant force. Okay, constant force. Okay, this is we have only one from 0 to in this line. Okay, using only in this line. So you have 0 to A and then A2, and then you have force with alpha, and then you have here delta x. Okay, this is delta x. So work done from 1 to 2 is F. Okay, work done from 1 to 2, okay, equal to, again you use the equation F cosine alpha. Okay, put in bracket and then times delta x. Okay, this is case where work of a constant force. The next one is related to the gravity. Look at here, the gravity. What will happen from here to here, right? It cannot be from here to here unless we have the put a power here, put a motor, and then move upward, right? If using gravity, it's going down like that. Okay, so A2 and A1 and Y1, Y2, and this Y. Y is variable, right? So from here to here, from one location to here, this is dy, right? Differential in y, right? Differential in y. So for work and energy, work of force of gravity, we have here. We have du equal to fx dx plus fy dy equal to, so we take the datum, going down, okay? So we have a minus w, okay? Minus w dy. So work done that we have here is work done from 1 to 2. We're going to have minus w delta y, okay, delta y, which is here. Okay, so I would like to make a quick comment of this one, which is work of force of gravity. So work done by weight equal to product of weight w, okay, and vertical displacement delta y. Okay, so work done by weight is positive. Okay, so it is positive when delta y is less than 0. Okay, which is the body will move down. Okay, it move down. I think I'm going to stop here. Okay, because in our next class we're going to cover the topic of work of spring. Okay, what work of the spring. Okay, if you have any question, can. All right, do you have any question? If no question, I would like to show you a bit on the what's in the our class assignment that you have to do. Okay, which is here. You can download it and then submit, which is here. Over here you have the review of key concept of kinetic of particles. Okay. Okay, and then this is a unit of force. Okay, force, acceleration, and mass. Okay, and these are the unit vector that been used. Okay, this is a general understanding and basic concept. Okay, you can answer this. Okay, just to gauge your understanding, okay, understanding of the topic, okay. Multiple choice question. These are the conceptual understanding, okay. What kinetic is all about, advantage of using Newton's second law, okay, exercise using a free body diagram and effective force diagram, and then the analysis part. Yeah. So the way we set up this tutorial is similar to test, quiz, and exam. Okay, we call ODL exam. Okay, we have 2 ODL exam. So this is the analysis question. Okay, this is related to block diagram, or to block pull along the ramp. We discussed last time in our last class. Okay, this is related to pulley system. Okay, pulley system. Okay, also pulley system. This one, the one that I discussed last time. Okay, the RAM problem. Okay. This one is related to one that we discussed today. Okay. All right. This one also. This is in the later chapter. We didn't talk about it yet. Okay. This is today. Next week. We didn't touch this topic yet. Okay. Impulse momentum is next topic. So you can start to do it and then try to submit. Not try to submit. You have to submit by end of this month. Upload in the system. Okay. So I think that's all for today. Thank you so much. I'll see you next week, inshallah. If you have any question, you can write down at our wallpaper of the classroom, wall of our classroom, okay. Google Classroom, okay. And then I'll see you next week. Thank you so much. Sekian, wassalamualaikum warahmatullahi taala wabarakatuh. Don't forget to sign in your attendance.